Welcome friends. Myself Rahul Thakkar from LJ Institutes of Engineering and Technology. In the current video lecture series, we are studying the subject of Physics Group 1. Till now in the chapter of superconductivity, we have learned what are superconductors, its discovery and properties of superconductors. Also, we have learned about the factors to define a superconducting state and types of superconductor with few numericals based on the properties of superconductors, along with the BCS theory and coherence line. To get this, refer to my previous video lectures. You will be able to know about this much topics. After knowing the topics, you can move further to the today's video, which we are covering with the topic of London's penetration depth. So, without wasting any time, let's start with the today's topic, that is London's penetration depth equation. But before that, let us discuss what is a penetration depth. Okay, so it is a concept proposed by London's brother in the year 1935 that describes the Misner effect and zero resistivity by adding the two conditions, that is E is equals to 0 and B is equals to 0. Means electrical field is equals to 0 and magnetic field is 0 to the Maxwell's electromagnetic equation. These two conditions are applied to the Maxwell's electromagnetic equations. So what does this signifies? So it describes Misner effect and zero resistivity. How does it signifies? So it uses Maxwell's electromagnetic equation. So what is London's theory? So according to the Misner effect, the magnetic field lines do not penetrate the superconductor. Experimentally, the Misner effect does not occur abruptly at the surface, and London theory predicts that the magnetic field lines penetrate slightly in the bulk of the superconductor and then exponentially decay. Okay, it enters to the superconductor bulk and thereby gradually it starts decaying exponentially. So let us define. So in a superconductor, the London's penetration depth characterizes the distance to which a magnetic field penetrates into a superconductor, or the exponential decay of magnetic field at the interior surface of the superconductor. So this is the definition of London's penetration depth. So for understanding, let us consider a magnetic field Bx. Assume Bx is equals to, so Bx is equals to B0 into e raised to minus x by lambda L, where x is the distance inside the superconductor from the surface, B0 is the magnetic field at the surface, and lambda L is the penetration depth. So when lambda L is the distance across which the magnetic field becomes E times weaker, magnetic field becomes E times weaker. So which is formulated as lambda L is equals to under root of m by mu 0 n q square, where n is the charge carriers of the mass m, n is the number density, q is the charge, and mu is the absolute permeability. So you can see in the figure, initially Ba is the applied magnetic field. At a distance x, the magnetic field reduces gradually, or we can say that exponentially. So B inside is equals to Ba into e raised to minus x by lambda L, where B inside is the magnetic field inside the superconductor, Ba is the magnetic field applied to the superconductor, x is the distance inside that, and lambda L is the penetration depth. Okay, so let us discuss the London's equation. So before that, it is applicable to the Maxwell's theory. So let us discuss Maxwell's equation first of all. So Maxwell's equation fails to explain the existence of a Misner effect and zero resistivity in a superconducting material. In 1935, the London brothers added two more equations to the existing Maxwell equation to explain the Misner effect and zero resistance. Let us first consider the magnetic penetration depth in the context of London's theory. If magnetic field is applied to the superconductor, which is initially in a zero field, the magnetic field is a function of time. According to the Maxwell's equation, the time varying magnetic field gives rise to an electric field. So, thereby we can say that del into E, that is the curl of E, is equals to del B by del T. Remember here very carefully, over here the del, that symbol nebula, that is inverted triangle, you can understand that. It is termed as a nebula or del. Okay? I will prefer del everywhere over here. It is nothing but a differential operator. Its value is I del by del x plus j del by del y plus k del by del z. It is a differential operator for the 3 dimension and its symbol is inverted triangle. It is termed as del. So del into E, that is over here is a cross product. You can see the cross product is there, which is also termed as curl of E. I may recall it CURL. Curl of E is equals to del B by del T. Now, in a normal metal, this will induce eddy current, but in a superconductor, this field will give rise to the persistent current. Persistent current is also known as a supercurrent. This supercurrent in turn produces magnetic fields of their own, which opposes the applied magnetic field. Okay? So if applied field is weak, the flux is totally expelled from the superconductor. This phenomena is known as a perfect diamagnetism. So from the Newton's law, the equation of a motion for a superconducting carriers with a mass m and the charge minus E in presence of electric field E is given as F is equals to m dvs by dt is equals to minus E into capital E, where Vs is the velocity of superconducting carriers. The field induced, so let us give this equation as equation 1. Okay, so F is equals to m dvs by dt is equals to minus E into E. That is equation number 1. Now the field induced supercurrent density is given by Js is equals to minus small e into Ns into Vs, where Ns is the density of superconducting carriers. Remember, this is the equation number 2. Okay? Now from this equation 1 and 2 on comparing, we get dJs by dt is equals to Ns e square into E by m. Let us call this as a third equation, and this is nothing but the London's first equation. Remember this thing, del Js by del T is equals to Ns e square into E by m. This is the London's first equation. Now taking curl on both the sides of the equation 3, we get, I have clearly told you earlier about the curl. Curl is nothing but the differential operator. Okay, so applying differential operator on both the sides, and on subjecting E on one side, we get the equation as, you can see it over here, I may recall it, m by Ns into E square, that is the coefficient, we have taken it out as constant outside the operator. Now curl of del Js by del T is equals to curl of E. Let us give this as the equation number 4. Now the equation 4 can be rewritten as Maxwell's equation, that is, we know that curl of E is equals to minus 1 by C into del B by del T as we have discussed earlier. So now MC, on substituting its value in the previous equation, we get this equation number 5, M into C by NS E square into curl of del J by del T plus dB by dt is equals to 0. Now to obtain the Misner effect, we know that B is equals to 0. Magnetic field inside the superconductor must be equals to 0 in order to obtain the Misner effect. Okay, so in the bulk of superconductors, the magnetic field B is equals to 0 is the necessary condition to obtain the Misner effect. The London brothers removed the time derivative in the equation 5 and postulated a new equation. Okay, so the above equation, equation 5, on removing the time derivative, we get mc upon ns e square into curl of js plus b is equals to 0. So this is nothing but the second London's equation. This is the second London's equation. Now the supercurrent density is related to the magnetic field D by another Maxwell's equation. We know that Js is equals to C upon 4 pi into curl of B. This is the second Maxwell's equation. First Maxwell equation was curl of E is equals to minus 1 by C del B by del D. Now second Maxwell equation is Js is equals to C upon 4 pi into curl of B. On substituting the value of this second Maxwell equation in this second London's equation, we get mc upon ns into E square is equals to curl of C upon 4 pi into curl of B plus B is equals to 0. This wording is quite difficult over here for understanding, but carefully listen to my voice and look on the screen for the equation, so you will be able to understand this thing. Okay, so on simplifying, we get m into c square by 4 pi ns e square into curl of b. Over here 2 times differential operator is applied, so we can say that it is a curl of b plus b is equals to 0. So this term m into c square by 4 pi ns e square is termed as a lambda square, a lambda L square. Okay, so on substituting its value, lambda L square into curl of b plus b is equals to 0, where lambda L whole square is equals to mc square by 4 pi ns into e square. So that is nothing but the equation of London's penetration depth, lambda L. So we can say from the above equation that the penetration depth is proportional to the superfluid density. So that was all for this video, guys. Now in the next video we will learn about the application of the superconductivity in various fields. That's it for today, guys. Thanks for watching.